Hi students, Professor Nugent here. In this video, we're going to discuss specification problems with multiple regression. If we over-specify a model, that's not going to be such a problem. Specifying a model implies including a variable in an estimated regression that doesn't actually enter the population model. In that case, if the variable doesn't actually enter the population model, then the coefficient on that variable is 0, and we're going to get an estimated coefficient of approximately 0. The only problems that we may encounter there is higher variances in the other estimated coefficients. However, under specification is a much bigger problem because we may experience we may see omitted variable bias. So if we suppose that our population model is this equation here, y equals beta naught plus beta 1 times x1 plus beta 2 times x2 plus u, and suppose that for some reason we don't have data on x2. So we're just going to run a regression with x1. And that's this regression with tildes here. Y tilde is equal to beta naught tilde plus beta 1 tilde times x1. And we have discussed that this coefficient beta 1 tilde contains the unbiased estimate of beta 1 plus the unbiased estimate of beta 2 times this extra term, delta 1, which is the coefficient of a regression of x2 and x1. So we have this composite of coefficients contained in this beta 1. And so what we're going to have in this beta 1 is a biased estimate because we left out x2, so we are having omitted variable bias. The only time that we won't have omitted variable bias, so there are no omitted variable bias if beta 2 hat is equal to 0 or delta 1 hat is equal to 0. Beta 2 hat equal to 0, so this is if the variable x2 does not enter the population regression model and therefore is not contained in U. Delta 1 hat would be equal to 0 if x1 and x2 are uncorrelated, perfectly uncorrelated. All right, so let's specify the omitted variable bias if, in fact, this is our population model, but we actually run this equation. Let's specify that omitted variable bias. So the expected value, what is the expected value of beta 1 tilde? That's the expected value of beta 1 hat plus beta 2 hat times delta 1 hat. Now this is equal to the expected value of beta 1 hat plus the expected value of beta 2 hat delta 1 hat. And observe that this is equal to beta 1 plus, now, because expected value of beta 1 hat is equal to beta 1, expected value of beta 2 hat is beta 2, and delta 1 is just a function of the x's, which are non-random. We're treating these things as fixed and repeated samples, so this thing can come out of the expected value. So this is beta 2 times delta 1. So this is the expected value of beta 1 tilde. Now the bias in beta 1 tilde is equal to the expected value in beta 1 tilde minus beta 1, which is equal to beta 2 delta 1. So this is the amount by which our coefficient is going to be biased if we leave out that variable x2. And again, we're not going to have this bias if beta 2 is equal to 0. So if x2 doesn't actually enter the regression model, population regression model, or if delta 1 is equal to 0 if x2 is uncorrelated with x1. So we need two conditions for there to be omitted variable bias, X2 must enter the population regression model, or X2 must be contained in U, the factor must be contained in U, the factor must affect Y, and X1 and X2 must be correlated, related. They must be related, more general. All right. Now we can identify whether the bias is going to be upward or downward based on the correlation and the sign of the coefficients. So let's write down a matrix core x1, x2 positive, and let's have core x1, x2 negative. And let's say here we have if our coefficient is positive, then we're going to have positive bias. In this case, with the correlation being negative, and if beta 2 is positive, we'll have negative bias. In the case where beta 2 is negative, correlation is positive, we will have negative bias. And the case where beta 2 is negative and the correlation is negative, we're going to have positive bias. Let's take a look at an example. Again, let's work with our wage equation is equal to beta naught plus beta 1 times education plus beta 2 times ability plus U. So let's say this is the population model. Education and ability are important for wage. Education and ability are positively correlated. And let's assume that these coefficients are positive. Beta 1, beta 2 are both positive. The higher your education, the higher your wage. The higher your ability, the higher your wage. But plausibly, we don't have a data on an individual's ability. So we actually run this equation. What's going to be the bias in beta 1 tilde? That is equal to beta 1 hat plus beta 2 hat times delta 1 hat. And because the correlation is positive, right, and the coefficient on beta 2 is positive, we're going to have positive bias. So this implies that beta 1 tilde is going to be greater than beta 1 hat. So you're going to see something of a larger effect predicted in this equation than there actually is, because what you're getting is both the effect of education and ability together in this tilde coefficient. And what we need to do is figure out a way to control for ability so that you can get the true partial effect of education on wage, so that when you see a predicted change in wage given a 1-year change in education, you know that that is all else equal. Stay tuned to the next video when we generalize the omitted variable bias.